Okay. So, the previous class we gave you a definition of DTFT, we told you how it comes, that is if you input an e to the power j omega n kind of sequence at the input, then output becomes the same thing, but multiplied by a constant h to the power j omega, okay. And that is a function of omega. For various omegas, it will take different values, it is complex in general, that is called the discrete time Fourier transform. And given that, you can from that you can get back the sequence h n by inverse relation. And the question point is, I mean why only for h n? You can carry out a similar summation for discrete time Fourier transform for any sequence, not necessarily a unit sample response of a system. Because when I give you a formula summation, okay, when I give you a formula for this kind of formula for discrete time Fourier transform where a is e to the power j omega, why only h? It can be any sequence for which I can run a sum like this. It will be called the DTFT, discrete time Fourier transform of that sequence, and you can get back that sequence by the inverse transform relation. Like for h n, you can get it back from its DTFT like this. For y n, you can get it back like this. For x n, you can get it back like this. Capital X to the power j omega DTFT instead of capital H, capital X here. Then the same eigen sequence to the power j omega d omega integral minus pi 2 pi 1 by 2 pi. We have also seen that output DTFT from this comparison of the two integrals, this is y n directly and this is y n in terms of again a similar integral, but in terms of capital X to the power j omega, capital H to the power j omega. You can comparing, we wrote here that output DTFT y e to the power j omega is a product of the two DTFTs, one of the unit sample response of the system and another of the input, okay, which means convolution of the two sequences in time domain, that is in time domain. In digital frequency domain is amounts to product of the two DTFTs, then you get the output DTFT. All right, that is where I stopped. Okay. This function for any sequence we write like this: if x n that is this given, you can see this entire function firstly complex. If you want to plot it versus omega, this function has got a real part and imaginary part. Okay, that is real part of this DTFT plus j times imaginary part of this total function, right. Or alternatively mod in the polar form, this is a rectangular form, a plus j b, that kind of form for a complex number, and this is you can alternatively write it as polar form, that is magnitude times e to the power j angle of, this is a phasor polar form. Now, in either way you see, if you want to plot this capital X e to the power j omega vis a vis omega, you need to plot two things, like here you need to plot the magnitude part as a function of omega and phase angle as a function of omega. Two things are required, then only you get a complete description of x. Alternatively, in this form, rectangular form, you again need to plot the real part of this DTFT versus omega, and again you have to plot imaginary part of DTFT versus omega. Then only you get a complete picture. Okay. Now, often, and especially in the case of this polar form, we might just take care of the magnitude plot, do not show the corresponding phase response plot, phase, that is phase part versus omega, but whatever logic we say with respect to this magnitude response, same will be applicable for this, that can be easily seen. Okay. But technically a complete plot of DTFT versus omega, that is frequency response or spectrum we call it DTFT spectrum of x m, which is this plotting of this DTFT versus omega, that actually always requires two plots, one of magnitude versus omega, another is phase versus omega, or equivalently one of the real part, one of the imaginary part versus omega. Although between the two we normally prefer this polar form. Now, this function DTFT, suppose omega I replace by, omega is radian, right, its digital frequency unit is radian. So, this radian plus another 2 pi radian. If I replace omega by that, what happens to the right hand summation? RHS becomes j omega plus 2 pi r, and then e to the power minus j omega r as it is, but e to the power minus j 2 pi r. E to the power minus j 2 pi r is always 1 for r, because r is an integer. E to the power j 2 pi, e to the power minus j 2 pi, e to the power j 4 pi, e to the power minus j 4 pi dot dot dot, they are all having value 1. All right, this I believe you know. So, you will get back x of r e to the power minus j omega r, which is nothing but your original DTFT, which means DTFT here if I replace omega by omega plus 2 pi, okay, I get back the same thing. So, this is periodic, over omega. So, if you take the magnitude and phase, I am normally plotting like this, but this is wrong. I should plot mod versus omega, I should plot angle versus omega, but just to make my point, I am just plotting it, any plot versus omega, say maybe pi here minus pi here. Then if we extend from pi to 3 pi with 2 pi here and minus 2 pi minus 3 pi, minus 2 pi, minus 4 pi. Here again the same thing, minus pi to pi, next period is pi to 3 pi, right. So, it will be repeated, minus pi to pi one period. Okay. I think I will redraw it, this I made some mistake here, the boundary is not correctly done. Suppose minus pi to pi, that is one period, then pi to 3 pi, minus pi to minus 3 pi. So, whatever you have here, that will be repeated over this, over this. So, if you have things like this, suppose, then again here there will be a gap, it will be like this. Here it was 0, so next center frequency will be 2 pi, here it was 0, next center frequency will be minus 2 pi. So, there is a gap, because this gap and this gap. So, on this side also this gap. The same thing from minus pi to pi, that gets repeated here like that. So, it will be like this, continue. It is a periodic function of omega. Normally, it should be magnitude versus omega and parallelly phase versus omega. Another plot phase versus omega, both will be periodic over omega over a period of 2 pi. Normally, we do not put a magnitude, sometimes just write this to indicate that I am indicating both, but that is actually technically wrong, because I should have magnitude separately, phase separately. But nevertheless, this does not matter, because my point is here is to show that it is periodic on omega. So, for that I just plot capital X e to the power j omega right here, okay, because the argument is clear. The same logic, if I write as magnitude here and phase here, same logic will be right there. All right. So, that is one property, important property. Then another thing which you have already seen, that if there is a convolution, suppose x n convolved with h n, you get y n, that y n is x n convolved with h n, or equivalently h n convolved with x n. We have seen by comparing two integrals, that output DTFT is product of the two DTFTs, but this we can work out directly. what is between the two convolutions, as I told you earlier, as I have been telling you, I will prefer this form. So, if you take that form, it will be H r x n minus r. Okay. So, this is y n. So, what is y e to the power j omega? If I compute directly, y n e to the power minus j omega n by the DTFT formula, y n e to the power minus j omega n, that is directly you can compute the DTFT, but this y n now I replace by this much, that is this summation comes. This comes, and then outside e to the power minus j omega n. Now, you have a double summation, as I told you in DSP, whenever you come across double summation, next step is to interchange the two. So, this summation suppose comes out, and inside you have got summation over n. H of r, it does not depend on n. So, this quantity can come out as common. You have got x n minus r, it remains inside. First I interchange the two, then from inner summation H r comes out, because inner summation now is with respect to n, is H depends on r, not on n. So, it can come out as common, and inner I have got x n minus r, that depends on n. So, it remains e to the power minus j omega n, that depends on n. So, it remains. This is the thing. Now, I have got n minus r, and I have got e to the power minus j omega n. Suppose I want to make it n minus r. So, I have brought an extra term e to the power minus j omega minus r, that is e to the power plus j omega r, I have brought in here. So, I have to cancel it. So, I should have e to the power minus j omega r, and this means this total thing, they depend on n. This depends on n, this depends on n, but this fellow does not depend on n. So, it can again go outside this first summation, inner summation as common. So, it will be r h of r e to the power minus j omega r and summation now n minus r, you can give a name m. So, if n is minus infinity, m also minus infinity. R is fixed from outside, so R is a constant in the inner sum, because R is coming from here. Once you choose R, when you go here, R is fixed. So, R has a fixed value. N is varying from minus infinity to infinity. So, as n goes to minus infinity, m also goes to infinity, minus infinity. And when n goes to plus infinity, this also goes to plus infinity. So, I write in terms of m, n minus r, I write as m, this is m now. Now, what is happening? In the outer sum, first you choose a r, then carry out the product h r e to the power minus j omega r, hold it. Then for that r, you run this summation. Then choose another r, carry out this product, then hold it. For that r, again run this summation. But this summation is independent of r. Now, it is m. For any, this summation is what? You can see this is nothing but DTFT of x m. For any m you choose, summation minus infinity to infinity e to the power minus j omega m. Okay. So, you get this, and this again does not depend on r. This summation is a constant, independent of r, independent of any index. So, this will go outside. So, this inner, it remains. This remains as it is. But what is this? This is again DTFT of Hn sequence. So, this is a product of, then I get the proof directly. All right. This DTFT is nothing but product of the two. This is direct proof. Earlier we just arrived at that by comparison of two integrals. So, that means output y n is an inverse, we have already seen this, I am rewriting, is an inverse DTFT of and you can write as this. This has a good physical interpretation. You see, this is the sequence, because this is dependent on n. Okay, this is the sequence. The integral is with respect to omega, that is, you are carrying out this is the amplitude of the sequence. This is like a carrier e to the power j omega n is like the time axis, instead of time it is just an index, but it is pointing to the time axis, just discretized, and it is multiplied by an amplitude which is independent of n. And you are superimposing several such carriers by varying omega continuously, not only one frequency, but various frequencies continuously over this patch, and then adding all of them. So, it is a superposition of various carriers of continuously varying omega. Okay. Now, this amplitude part, one is coming from input, okay. Another is by your design. So, magnitude of the amplitude is okay, this is the magnitude of the amplitude. Then there is an angle part will get added with this. Okay. This you see magnitude part here, you can make it large, you can make it small by choosing this large or this small for a particular omega. For certain range of omega, you can make the magnitude of this response DTFT large, and for certain ranges of omega, you can make this small, which means input DTFT will be amplified for certain ranges of omega, and they will disappear, they will become 0 or very small in certain other ranges of omega, where you design your system to be such that the corresponding DTFT mod DTFT has very low value, almost 0 at those ranges of omega. This gives rise to the idea of filtering, that input may have this mod x e to the power j omega high at all values of omega from minus pi to pi. This is the range for any DTFT minus pi to pi. Suppose it has high value, same value, but I can design my H so that maybe over a range it has high value, and then remaining range it has 0 value. So, when I multiply and then take the integral from minus pi to pi, only maybe from minus omega c to omega c some value, only this matters, because only during this part input function, input DTFT, and therefore, its magnitude will be multiplied by the system response DTFT magnitude. So, this part is non-zero, because this multiplied by this, but this range of omega, whatever be the input DTFT value, we call it spectrum, that will be multiplied by 0. So, those frequencies will not go through. In the integral, they will be contributing nothing. So, output DTFT will be just a product of the two. So, this part is absent, this part is absent. This is the idea of filtering, that pass certain frequencies and do not pass certain frequencies by designing this mod h to the power j omega accordingly, and thereby you know the idea of band pass filter, low pass filter, high pass filter, these things come. Okay. The next thing, I have assumed this summation DTFT it exists all right, but you see this is an infinite summation. So, infinite summation doesn't means that its magnitude of the summation may converge or may shoot up to infinity. If it does not converge shoot up to infinity, then DTFT does not exist, at least for that omega you have put in, it does not exist. For DTFT to exist, mod of this for all omegas should be finite. there is mod of this should be finite. Now, I told you the other day I have done mod of a summation using the triangle inequality. You can write mod of a summation less than equal to summation of the mods. So, this is less than equal to summation of mod over this, and mod of a product is product of mods, and mod of e to the power j omega n. But you see e to the power minus j omega n, its mod, there is magnitude is 1. So, this is nothing but now I want this left hand side to be finite, but left hand side is less than equal to this. So, if this is made finite, then obviously left hand side also be finite, and therefore, DTFT will exist. So, a sufficient condition for DTFT to exist is that the sequence, its mod value, and then if you sum, it should be finite, that the sequence should be absolutely summable. We have already come across this absolute summability in the context of stability. There is given a linear shift invariant system of impulse response H, unit sample response H n, system will be stable. A sufficient condition is that its unit sample response should be absolutely summable, that is, you take absolute value and then sum over all the n, it should be finite. This is a sufficient condition. If it is true, system is always stable. Though if it is not true, it does not mean that it will always be unstable, sometimes it can be stable also. Similarly, if this is finite, suppose this is finite, then this is finite. So, DTFT will always exist, but it does not mean that if it is not absolutely summable, there is a absolute value and summed. If it is shoots up to infinity, it does not mean that this LHS also shoot up to infinity, because it is less than equal to. So, right hand side can still be infinity, this can still shoot up to infinity, but left hand side can be less than infinity, that is finite. So, this is a sufficient condition that for DTFT to exist, for sufficient condition also called Dirichlet condition is that if you take the absolute value of every sample of the sequence x n and then sum the absolute values over all the indices, the sum should be finite, that is summable. If it is satisfied, this mod is less than infinity, the DTFT exists. But it does not mean that if it is not satisfied, DTFT does not exist, because this is less than equal to this. So, it can be less than the right hand side also, and if right hand side goes to infinity, still the less than sign will imply that left hand side is finite. It is less than or equal to. Equal to means left hand side also will be infinity, then does not exist, but less than means it may exist. But if the right hand side is less than infinity, this is finite, I am very happy, then DTFT always exists. This is a sufficient condition. All right. One important property is called Parseval's theorem. If I suppose take the mod value of every sample, square it up, it will give me the power, instantaneous power in that sample, and if I add over all of them, I will get a total energy in the signal. Okay. If the energy is finite, it is called energy signal. If the power is finite, but summation is not finite, I call it a power signal. Okay. Now, suppose this is given to you and it is an energy signal, so summation exists. Then I can write it x n into x star n, because mod x n square means like mod z square means z into z star. So, x n into x star n. Then x n I can replace by its inverse DTFT relation, and outside x star n. Then there is a double summation. Next step is to interchange the two summations, 1 by 2 pi goes out. minus pi to pi outside with respect to omega. Inner summation is with respect to n. Anybody which has a value which is dependent on n will be inside. So, e to the power j omega n will be inside, x star n will be inside. This guy does not depend on n, so it will be common outside, and d omega. Now, this summation see x star n e to the power j omega n, you can write it as x n e to the power minus j omega n star. Conjugate of a product is product of conjugates. We have seen the other day, again I am reminding you. Suppose Z1 is R1 e to the power j theta 1, Z2 another complex number R2 e to the power j theta 2. So, you have got Z1 Z2 as Z, you have got R1 R2 e to the power j theta 1 plus theta 2. You have got Z star, that is star of a product, it will be R1 R2 e to the power minus, this will become minus theta 1 plus theta 2, which is same as R1 e to the power minus j theta 1 R2 e to the power minus j theta 2, which is Z1 star Z2 star, right. Z1 star means R1 e to the power minus j theta 1 R2 to the power minus j theta 2. So, star of a, these are basic things you should know, but I am not taking any chances. So, I am carrying it out. Okay. So, Z1 Z2 was Z, star on that is star of the product is product of stars. So, x star n e to the power j omega, and I can write like this, because star of this product means star here x star n and star here. So, minus will become plus. So, this summation star d omega, but what is this summation? DTFT. So, it will be for any omega x, capital X to the power j omega here and its conjugate here. So, this will be x star, with a star it will be x star e to the power j omega. So, x to the power j omega, x star to the power j omega, it will be minus pi to pi this shows that to calculate the total energy, if it is an energy signal, you square up the mod value of every sample, take the mod and then square it up. So, that is an instantaneous power of that sample, and then sum it over all the index, there is a total energy that you are computing in time domain. You can do the same thing in frequency domain. There is a mod value of the DTFT, square up and integrate over all omega from minus pi to pi, just multiply by 1 by 2 pi. This is called Parseval's theorem. It is very much useful in many contexts. I stop here today. I will continue from here in the next class.